At the beginning, running an application felt simple. There was one application, one server, and a small amount of traffic. If something went wrong, an engineer could log in, restart the process, and move on. Then the application became important. More users arrived. One server could no longer carry the load, so we added copies. That solved capacity for a while, but it also created a new job. Someone now had to keep all those copies running. The application also stopped being one thing. Teams split it into smaller services so they could build and release independently. Now each service had its own copies, its own version, and its own dependencies on other services. At this point, the hard problem was no longer starting a program. The hard problem was keeping the whole system in the right shape. Where should each copy run? What should happen when a machine fails? When should we add capacity? How do we release a new version without taking the service down? The natural response was to write scripts and runbooks. First, create a machine. Then copy the application. Then start it. Then update the load balancer. Then check whether it worked. This approach describes a sequence of commands. But a distributed system does not wait for the runbook to finish. A node may fail while a release is running. Traffic may rise while capacity is being added. Another team may deploy a different version. By the time the command sequence finishes, reality may already have changed. So the question had to change. Instead of asking, which command should I run next, we needed to ask, what should this system look like right now? That question leads to a very different style of automation. Instead of spelling out every step, we describe the result we want. For example, run 5 copies of the application, use version 2, keep them healthy, and make them reachable. Now compare that desired state with reality. We want 5 healthy copies on version 2. But the cluster currently has only 3 copies, one is unhealthy, and they are still running version 1. That difference is the real work. A reliable system can now work in a loop. Observe what exists. Compare it with what was requested. Take one corrective action. Then observe again. The loop does not assume that the world stays still. Kubernetes was one elegant answer to this class of problem. It placed the desired state at the center of the system and built continuous control loops around it. You declare what should exist. Kubernetes keeps watching, comparing, and moving the cluster toward it. Consider a failure. The desired state still says 5 replicas. If one pod disappears, the actual state drops to 4. The controller notices the gap and creates a replacement. No operator has to discover the failure and manually replay a runbook. The same pattern can handle other kinds of change. If the desired replica count becomes 8, the system adds capacity. If the desired image becomes version 2, the system replaces old pods gradually. Different operations, but the same feedback loop idea. This is what made the approach elegant. Kubernetes did not try to predict every possible failure or encode one enormous script for every situation. It created a common model, declare the outcome, observe reality, and keep correcting the difference. Kubernetes did not make machines reliable, networks perfect, or applications bug-free. Its achievement was different. It made recovery, scaling, placement, and rollout part of a continuous system rather than a collection of one-time commands. But this raises the next question. If Kubernetes is always comparing reality with the desired state, who is actually watching reality, and who decides what correction to make?